Hello. In this notebook, we are going to look at the transitions from NumPy to TensorFlow and Keras. It states that we will move from low-level tensor operations to high-level neural network APIs. So you can see the overview. It states why TensorFlow and Keras and what we are going to learn from the notebook. First, we start with the setup and imports. This block imports TensorFlow STF, imports NumPy, imports Matplotlib, sets random seeds, print TensorFlow version, checks available devices. And the output shows TensorFlow version, whether GPU is detected, device information. So this confirms our environment is set up. Next come the markdown that explains scalar OD, vector, matrix, high dimensional tensors. Then we can see the next block that is creating tensors. This block demonstrates tf.constant, tf.zeros, tf.ones, tf.random.normal, tf.I, tf.range. Each tensor is printed. The output shows tensor values, shapes, data types. This demonstrates basic tensor creation in TensorFlow. Then we have tensor data types. So this block basically shows different TensorFlow data types, casting between types using tf.cast. And as you can see in the output, it shows type conversions, tensor values before and after casting. Then we have device management that demonstrate checking for GPU devices using tf.device to place tensors on CPU or GPU. And the output confirms with devices where tensor is allocated. Then we have tensor operations. In this block, we perform element-wise addition, multiplication, matrix multiplication, transpose, and reduction operations like TF reduce sum, TF reduce mean, and the output prints resulting tensors and scalar reductions. In the next block, we have reshaping and broadcasting. It uses tf.reshape, tf.random.normal, tf1s, tf constants. The output shows shape changes resulting tensors after broadcasting. And we have variable and constants. In this block, we shows difference between tf.constant and tf.variable. Then demonstrates updating variable values. Here the output confirms variable can be reassigned, constants cannot be. Then we again have a markdown that is introduction to E in sum. This explains tf.E in sum conceptually. We don't have an output for this. Then comes the E in sum fundamentals, which uses ij and ji transpose. Output shows transpose, sum all, column sums, diagonal, trace. Then we have products and multiplications. It uses ii for dot product, as you can see here, and ij, jk, ik for matrix multiplication, that is shown here. If the output matches standard results, you can see the dot product, outer product, element wise matrix multiply in the output. Then we have batch operations. Batch operations demonstrate batched matrix multiplication using E in sum. The output here shows result tensor shape, correct batch multiplication. Then we have enum cheat sheet. This prints multiple E in sum examples. Outputs confirm different tensor multiplications. This markdown explains that gradient tape replaces manual backprop. Here we are setting the gradient. Output shows gradient is equals to 7. This matches analytical derivative. Then we have computation graph example. This blocks build a small expression graph, uses gradient tape to compute gradients of composite operations, and this output prints gradient values that we can see here 64 and 32. Then we have gradients with vectors and matrices. Uh, yeah, so this block demonstrates gradient of vector loss and matrix multiplication. The output here shows gradients with vector matrices and the shapes. Then we have important gradient tape patterns. This shows persistent tape, watching tensors, multiple gradients. You can see the different gradient tape patterns here. We have watching constant, persistent tape, high order gradients. Then we have TF dot function and graphs. This wraps a function with at TF dot function that shows graph execution, faster execution, and structure tracing. The output prints traced function results. Next, we have visualizing gradient descent. This implements manual gradient descent loop, prints loss values across iterations, and the output you can see it shows charts of loss decreasing over steps. This demonstrates optimization. In the next markdown, this states that neural network will be built without Keras. Then we have activation functions that defines ReLU, sigmoid, 10H. Output prints activation function output for sample inputs. So for the given inputs, we have the sigmoid values, the ReLU values, and the leaky ReLU. Then we have loss functions that defines MSE binary cross entropy. Output shows loss value for sample predictions. You can see the MSE loss and BCE loss values here. Then we have neural network from scratch. This block defines weights as TF dot variable, forward pass manually, loss computation, gradient computation using gradient tape, parameter updates. So in the output, we can finally see loss decreasing over epochs. Then we have XOR problem. This trains our network on XOR data set. In the output, you can see predictions, loss improvements. You can see the loss XOR training graph. So this is showing us the loss improvement over the epoch values. Then we have markdown into Keras that explain transition from primitives to Keras abstraction. Next cell demonstrate layers.dense explain. This create a dense layer. It shows input shape, output shape, trainable weights. Output prints layer summary. Then we have sequential API. This defines model using keras.sequential. And the output prints model summary, model created with sequential successfully. Then we have functional APIs. This define model using keras.model shows flexible architecture and the output prints the summary. Subclassing maximum control. This defines custom model class inheriting from keras.model. Output confirms forward pass. We have compiling and training. This compiles model optimize loss and matrices. The output shows epoch-wise loss and accuracy. In the next cell, we can see dynamic architecture builder, where it creates model dynamically based on parameters. Output prints model summary. deep net without dropout, and batch norm. The small net 281. This was dynamic architecture builder. Then we have complete training examples or with Keras. In this block, we train XOR model using high level API. The output shows again the predictions improving with epoch, loss decreasing with the corresponding epoch values. Then we have moons classification. Again, we load synthetic data, synthetic moons data set. We train the model here by splitting it, and the output shows it shows training logs, the training progress and accuracy. Then we have visualizing decision boundaries, plot classification boundaries. Output shows decision surface separating classes. You can see the distinction here between the different classes and the prediction chart. Then we have digit classification. Here again, we load digit dataset, train dense neural network, and the output shows accuracy metrics and the loss function with respect to epoch curve. Then we visualize digit predictions, plot digit images, and predict labels. Output shows correct and incorrect classification that you can see in these images. And we have callbacks. Callbacks demonstrate early stopping, model checkpoint. And the output shows callback behavior, common callbacks during training. Early stopping, model checkpoint, reduce LR on plateau, tensor board, learning rate scheduler. The markdown shows comparison summary, prints comparison table between NumPy, TensorFlow, primitives and Keras with respect to different aspects, backpropagation, GPU, TPU support, weight management, gradient computation, etc. Then we have Keras versus PyTorch comparison, shows the structural differences, output prints comparison summary with respect to different aspects between Keras TensorFlow versus PyTorch. Then we have best practices. This prints best practices guidelines. Then in the next we have cheat sheet that prints quick reference commands. Then next we have the conclusion markdown that summarizes our entire journey. So this was all about this notebook. Thank you for listening to this video.